Good day, everyone. Today we'll be diving into one of the foundational results in number theory, Fermat's little theorem, a brilliant discovery by the renowned French mathematician Pierre de Fermat. So let's start by understanding the context. Pierre de Fermat, often referred to as the father of modern number theory, made numerous contributions to mathematics despite being a lawyer by profession. So he had a habit of writing his ideas in the margins of books, often without giving detailed proofs. So Fermat's little theorem is one such result that he shared in his correspondence, leaving future mathematicians to verify and explore its implications. So now, what does Fermat's little theorem state? It tells us that if p is a prime number and a is an integer that is not divisible by p, then when a is raised to the power of p minus 1, the result when divided by p leaves a remainder of 1. So mathematically, this is expressed as shown. I'll show a picture above. So this theorem might seem like a simple statement, but it's incredibly powerful. It gives us a way to understand the behavior of integers under modular arithmetic, especially when working with prime numbers. Fermat's little theorem also serves as a building block for many advanced topics in mathematics, including Euler's generalization of the theorem and concepts in group theory. So what's truly remarkable about this theorem is its relevance to modern application. For example, it plays a crucial role in cryptography, particularly in the security algorithms that protects our digital communications. Without results like Fermat's little theorem, many of the encryption system we rely on today wouldn't exist. So with this brief introduction, I'll now hand it over to my group members who will delve deeper into the theorem's proof, examples, and applications. Thank you.
Fermat's little theorem states if p is a prime number and a is any integer such that GCD AP is equal 1, then a power p to the power of negative 1 is congruent to 1 mod p. This theorem has important implications in modular arithmetic and number theory. The two claims in our example relate to properties of numbers in modular arithmetic. Claim 1. GCD Kn is equal 1 and I times E is congruent to G times E mod n and I is congruent to G mod n. Explanation. When GCD Kn is equal 1, K has a multiplicative inverse modulo n. Let this inverse be K to the power of negative 1 such that K to the power of negative 1 is congruent to 1 mod n. If I times k is congruent to g times k mod n, multiplying both sides by k to the power of negative 1 cancels k. I times k negative 1 is congruent to g times k to the power of negative 1 mod n times I is congruent to g mod n. This shows that multiplication by k when GCD kn is equal 1 is reversible modulo n. For the claim 2, if GCD kn is equal to 1 and I is congruent to g mod n, then I times k is congruent to g times k mod n. Explanation. This is straightforward since I is congruent to g mod n. We know I minus g is equal n times m for some integer m. Multiplying both sides by k, I minus g times k is equal n times m times k. This implies I times k is congruent to g times k mod n. For the special case prime modulus p, when p is a prime, k is not a multiple of p, and GCD kp is equal 1, claim 2 implies that 1 times k mod p, 2 times k mod p, and so on for p minus 1 times k mod p is a rearrangement of 1, 2, and so on p minus 1. All these numbers are distinct because of claim 1. Example, prime p is equal 7, k is equal 3. Let's calculate 1 times key, 2 times key, and so on, equals 6 times key mode P, where where P is equal 7 and key is equals 3. 1.3 mode 7 is equal 3. 2.3 mode 7 is equal 6. 3.3 mode 7 is equal to 4.3 mode 7 is equal 5. 5 times 3 mode 7 is equal 1. 6.3 mode 7 is equal 4. So the answer is 362514. Notice that this set is a permutation of 1, 2, 3, 4, 5, 6. Each number occurs exactly once, confirming the claims. So, the summary of this example, claim 1 ensures that multiplication by key is reversible modulo n when GCD kn is equal 1. For the claim 2, ensures that equivalent numbers remain equivalent when multiplied by key. For a prime p, the multiplication by key produces all distinct residues modulo p for a permutation of 1, 2, so on p minus 1. Thank you.
So each of the eigenmodes cannot be equal to 0 because p is a prime number. So let C1 equals to eigenmode p. So 1 is greater than equal to C1 and p minus 1. So 1 is greater than equal to C2, then p minus 1, so on and so forth. So by the above, we know that C1, C2, and quantity of p minus 2 and quantity of p minus 1 are all different. So for each I from 1 to P1, 1 to minus 1, there is exactly on Cg, such that Cg is equal to 1. Therefore, we know we have key mode P minus the quantity of 2 key mode P, the quantity of P minus 1 key mode P is equal to C1, the quantity of C1, C2 minus P minus 2 minus P minus 1 is equal to 1 times 2 times 3, and so on and so forth, P minus 2 and P minus 1.
Okay, now I will be discussing the proof of this example. So 1.2 and so on, open parenthesis, p minus 1, close parenthesis is equal to open parenthesis, k mod p times 2, k mod p, and so on. Open parenthesis, p minus 1, close parenthesis, k mod p, close parenthesis, mod p is equal to open parenthesis, k times 2k, and so on. Open parenthesis again, p minus 1, close parenthesis, times k mod p is equal to k p minus 1 and close parenthesis times 1.2 and so on p minus 1 mod p. So by cancelling 1.2 and so on p minus 1 on both sides of line claim 1, we can cancel them because the greatest common divisor of 1.2 and so on p minus 1 on both p 1.2 we have 1 is equal to k p minus 1 mod p. Now, someone will discuss the theorem of this proof.
For now, let's build in what this theorem is about. So, Fermat's level theorem says that if p is a prime number and then p does not divide a, then a to the p minus 1 is congruent to 1 on p. So let's consider this example. Consider that p is equals 5, wherein 5 does